So welcome everyone. This is a problem from 2000 JEE Advanced. It is problem of rotation. This is one of the problems that I admire a lot and I always wanted to make a video on. So let's read out this problem. I am reading out this problem for you people. Two thin circular discs of mass m and 4m. So we have two thin circular discs of mass m and 4m. Radii a to a. It has radii a, this has radii 2a, are rigidly fixed by a massless rigid rod of length root 24a. So these are fixed by root 24a. We don't have a rod after this and we don't have a rod after this. Okay. Through their center, this assembly is laid on a firm flat surface and set rolling without slipping. Important information we have here that it is undergoing rolling motion, rolling without slipping. Okay, on the surface, so that the angular speed about the axis of rod is omega. So we have been given the angular speed about the axis as omega. Okay, the angular momentum of the entire assembly about O is L. So total angular momentum about this point is our O, is L. We have been asked to see the figure which of the following statement is true. So we have been asked certain information regarding the angular momentum of this body. The first point is the center of mass of the assembly rotates about z axis with angular speed omega by 5. The magnitude of angular momentum of the center of mass of the assembly about point O is 81 ma square omega. The magnitude of angular momentum of assembly about center of mass is 17 m omega a square by 2. The magnitude of z component of L is ma square omega. So basically we have to deal with the angular momentum of this assembly. So we must understand how it is moving. It's very important to understand how it is moving. So if we have this rod, okay, we have a disc here, and it is spinning and rotating. Try and understand, it is spinning and meanwhile it is rotating too. It is spinning and meanwhile rotating too. It is spinning and rotating too. So it has a spin angular momentum and an orbital angular momentum. So whenever we write the total angular momentum of a body which is undergoing combined translation and rotation, we write it as L is equal to I center of mass omega plus R center of mass cross M V center of mass, where this term is called spin angular momentum and this term is called orbital angular momentum. In this case, what we are learning, when it is going like this, it was spinning and it was rotating too. The spinning thing gives its spin angular momentum and this motion gives orbital angular momentum about O. So basically, if we try to understand, this motion is basically giving it spin angular momentum, and when it is going like this, it is giving it orbital angular momentum. Let's find out few information regarding this. We have extended this to pass through the point O, where this length as mentioned in the question is root 24a. So this length becomes, this angle is 90 degrees, so this length becomes root 24a square plus a square, so this is 5a. Okay, so if we draw a triangle like this, so this is the triangle and we have this as root 24a, this as a, so this becomes 5a, this angle is theta. So we have cos theta is equal to base upon hypotenuse, that is equal to root 24 upon hypotenuse is 5. Similarly sin theta will be equal to perpendicular upon hypotenuse, that is equal to a upon 5a, that is equal to 1 upon 5. Further, if we calculate the center of mass from O, reference point O, then R center of mass is equal to M1 R1 plus M2 R2 upon M1 plus M2. So this will be equal to M into L plus 4M into 2L upon 5M, that gives out to be 9L by 5. So the distance of the combined center of mass, let's call this as combined center of mass, from O will be 9L by 5. However, its distance from the center of the smaller disk, let's call it as P1, and the other disk center as P2, will be 4L by 5. 4L by 5. So we have this information readily available. Okay. So in this case, the spin angular momentum will be extension about this axis about which it is spinning, and this extension, if we extend, okay, so we have a spin angular momentum. Let's denote it by L suffix omega. Okay, this is giving us spin angular momentum. This is our spin. Okay, and then since it is rotating about this, there will be an orbital angular momentum, but it won't be about z axis since it is not rotating. If it was rotating it like this, then it would have been about, if it was perpendicular to this and it was rotating like this, it would have been about z axis, but it is rotating like this, so it's not about z axis. It little bit offset from the z axis, and it's somewhere here. Let me redraw it. It is somewhere here, which is offset from the z axis. Let's call it by Arabic numerical L omega, Greek numerical L omega. This is offset from z by an angle theta because it will be perpendicular to this axis. L omega. Now we have certain thing to calculate for this. Let's calculate them one by one. I will be rubbing out this portion so that we have a space for the calculation. Now once we have understood it, the calculations are very easy and very feasible. We have to just understand there are two angular momentums, spin and orbital. Spin is about this axis due to this rotation, and orbital angular momentum is due to its rotation like this about point O. The first part of the question deals with the center of mass assembly rotates about z axis with angular speed omega by 5. The center of mass is not at all rotating about z axis. It is rotating about point O, so it has some omega about this axis, not this, but it will have a component on this axis. Okay, it will have a component on this axis. So we can write the component, we can calculate the omega of center of mass about this point and then take the component. How we will calculate the omega of this system about this axis? We know this point is undergoing pure rolling, so its velocity is 0. So by that concept here, V center of Vp1 plus omega A should have been 0. So this point must be having the velocity of omega A. So we can write Vp1 is equal to omega A. Further, it is also undergoing rotation with some angular velocity, Greek numerical omega. So we can also write it as omega into L is equal to omega small a is equal to Vp1. So we have omega Greek numerical is equal to omega A by L. But this is the angular momentum. This is the angular momentum omega about this axis. We have to take the component of this along the z axis. So the component of this omega along the z axis will be equal to omega A by L into cos theta, and cos theta we have as we have the value of cos theta. We will substitute this. Let's substitute the value omega into A upon L is root 24A, and the value of cos theta is root 24 upon 5, root 24 upon 5. So this gets cancelled, A gets cancelled, we are left with omega by 5. So this comes pretty well. The center of mass of the assembly rotates about z axis with angular speed omega by 5. Actually it's not rotating about z axis, it's rotating about some this axis which has a component along z as omega by 5. So this goes with the answer. This is pretty good, and this will be the answer. Okay, so A comes out to be correct. A comes out to be correct. Further, we have gotten information that the rotation of center of mass about this axis is Greek numerical omega, and its value is omega A by L. So I am mentioning this too, omega L, A by L. We might be using it further. Okay, moving on to the B part of the same question. Let's try and understand what is there in the B part of the question. The magnitude of the angular momentum of center of mass of the assembly about point O is 81 MA square omega. Now, what is the angular momentum of the assembly? Center of mass of the assembly. So, basically what they want us to calculate, R center of mass cross MV center of mass. They want us to calculate the orbital angular momentum of center of mass about point O. The magnitude of angular momentum of center of mass. So, we have been asked to calculate orbital angular momentum about point O. Okay, center of mass of the assembly about point O. So let's calculate it. We have the formula ready. R center of mass cross MV center of mass. So it will be orbital angular momentum. We have been asked to calculate R center of mass cross MV center of mass. But we won't be using this. V center of mass can be written as omega R. Okay, so this can be reduced to the form I of center of mass about O, because we are this R center of mass is taken from this point, so we can write it as I center of mass about O, and angular momentum, this is I center of mass about O multiplied by omega, where this omega is the angular velocity of center of mass about O. So this comes out to be, what is the total mass of the center of mass? It's 5. Distance of center of mass from O is perhaps 9L by 5. So a point rotating about a given point has angular momentum, moment of inertia as mr square. So m is this, r square we have to put a square, and omega we had already calculated as omega A by L. So let's put omega A by L. So this comes out to be 5m into 81 L square upon 25 into omega A by L. So one of the L gets cancelled, 5 gets cancelled to 5. We are left with 81 m omega. Okay, 81 m 9L by 5. So it was some L can be, so 81 m omega, we have a and we substitute the value of L, that is equal to root 24a. So this becomes root 24 a square upon 5. So we have got the angular momentum about this point, that is L omega, as equal to 81 m omega root 24 a square upon 5. We are writing it to, though it is quite tempting that we have a 81, we can mark it as 81, but the other part of this answer doesn't match, so this won't be a correct answer. This won't be correct. This was correct, this is incorrect. Moving on to the next part of the same question, which says the magnitude of angular momentum of the assembly about center of mass. So now we don't have to calculate the angular momentum of center of mass about any point. We have to calculate about center of mass. That means they want us to calculate the angular momentum of this assembly about an axis passing through center of mass. That means they want us to calculate I center of mass omega, which is spin angular momentum, that is angular momentum due to spinning motion. So let's calculate the spin angular momentum of this part. And spin angular momentum we already know. Spin angular momentum is equal to I center of mass omega, where this I center of mass is angular momentum of this system about an axis passing through center of mass. So this is basically equal to I1 plus I2 into omega, where I1 is the angular momentum of means moment of inertia of this smaller disk about this axis, I2 is the moment of inertia of this bigger disk about this axis, and omega is given in the question itself. So this becomes m a square upon 2 plus 4m into 2a square upon 2 whole multiplied by omega. This comes out to be 17m a square omega by 2, which correctly matches with the option given. So we have spin angular momentum about an axis passing through center of mass as 17m a square omega. So we can also write here as 17m a square omega upon 2. Okay, so let's move on further. The last part of the question. So this is correct, this one is correct. The last part of this question is that the magnitude of z component of L is 55m a square omega. See, we don't have any component, neither spin angular momentum is along z nor orbital angular momentum is along z, but both of them have a component along z. So we have to find that component. So let's find the component. So the component of L, we have to find the component of L about Z. So basically we have to find for spin, and let's find for first orbital. So orbital is L Greek omega Z component, that is this is for spin, spin Z component plus this is basically, sorry, this is not a spin, this is orbital. This is for orbital Z component. We have to take the Z component of orbital angular momentum, and then we will take the Z component of spin angular momentum. So we will take the Z component of, first we will take the Z component of this, which is cos theta and is positive, and we will then take the Z component of spin angular momentum, that is sin theta. If this is theta, this will be theta, so this will be sin theta. So it will be equal to, for orbital it is 81 m omega root 24 a square by 5 into cos theta, and cos theta we have to take the component of this along, this is cos theta, we will have to multiply, that is root 24 upon 5 again. And then we will have a minus sign, because this spin angular momentum have a component along negative direction, and it is equal to 17m a square omega upon 2. Sin theta is nothing but 1 by 5. On calculating what we get approximately, this is a bit of algebra is involved, we will get 76m omega a square, which doesn't match it with this answer, so this is wrong. So we have two correct answers, A and then we have C. B and D are wrong. So what was there in the problem? We had to calculate angular momentum and something about omega, angular velocity. What was different in this problem? Generally a body which is undergoing pure rotation motion, let's have a disc or a sphere which rolls on a ground, has both translational and rotational angular momentum, that is combined translation and rotation angular momentum, and spin angular momentum and orbital angular momentum. All of us or most of you would have gone through and would have analyzed the spin angular momentum and orbital angular momentum. You would have studied it. You would have gone through this expression several times. What is difference in this problem when compared to the other problem? In the general problem we come across, these two are along the same line, so their addition subtraction becomes pretty easy. However, in this case we realize that spin angular momentum and orbital angular momentum are offset and they are not along the same line, so the calculation becomes a bit difficult though interesting. So we had calculated for this, we had calculated omega was given about the axis itself, line one angle, and we had calculated the omega about the orbital angular momentum omega about this axis.
and it had a component along this, that is we can call it as omega z, and it was omega by 5. We calculated the orbital angular momentum, this part, due to the rotation of center of mass about O, and it came out to be 81 m omega root 24 a square by 5. Then we calculated spin angular momentum due to the rotation of this disk about the axis passing through the center of mass, that came out to 17 m a square omega by 2. Do let me know if you need any clarity about this in the comment section. Thank you a lot.